Wonderful. Thank you so much for inviting me. It's a really great pleasure to be here. I really enjoyed the morning session. Great. So what I want to talk to you today is about translating AI to brain and mental health. And actually how we can do this, but also the mandate we really have to be able to not only stay at the discovery space of multimodal AI, but translate it into healthcare. So that's the things I want to discuss with you today. So I'm sure I don't need to convince you that we really live in the space of and in the era of brain and mental health crisis, huge societal costs from diseases like dementia and brain and mental health disorders. 1 in 2 of us will be affected by dementia in about 20 to 30 years, and the annual costs are already huge, 42 billion pounds for dementia healthcare. So what is it that really we can do in terms of developing tools that allow us to change the healthcare pathway for individuals affected by dementia? I would like to focus primarily on early prediction. Why early prediction? Now we know that similar to cancer, with brain and mental health disorders, the earlier we treat, the better the outcomes. We also know that dementia starts in the brain 10 to 15 years before symptoms appear, and this is the best time not only to intervene with pharmacological treatments, but also by changing lifestyle factors. We know the Lancet has recently published 14 risk factors for dementia, and they all relate to things that I tell you to do, but I don't do. Sleep more, eat better, exercise. So really important, if we can predict early and personalize the interventions, then we are going to have better outcomes. But why is this so difficult? Why can't we do it? We have technologies that allow us to look into the brain and understand how the brain functions and understand how disease comes about. But still, it's a really hard problem to predict early when people have the very first symptoms or actually even before any symptoms appear. So the reason for that is, as I mentioned, 10 to 15 years actually before we see any symptoms, any changes in the behavior of individuals, we know that changes are happening in the brain. And therefore, during this early time, we don't have sensitive enough tools to detect these changes in the brain and predict the trajectory of individuals. The prognosis that individuals just get right now is, on the first symptoms, typically they will get a prognosis of 5 to 10 years of life expectancy. And this is too really general. It just generates more uncertainty to patients and their families. So we must do better. On top of it, the other complication we have is that dementia is not one disease. Dementia has many different subtypes that have very different symptoms and also very different pathology and biological underlying mechanisms. We have Alzheimer's disease, which is the most prevalent, but we also have frontotemporal dementia, Lewy body dementia, vascular dementia. So when we are considering a single patient, what we really need to consider is what dementia type they have, where they are in their trajectory, what stage they have, and of course there are many different markers that we need to take into account in making our decision. So this is a really complex space. We also know that the different markers, some of them are better in sort of giving us information about the type of dementia, some others are better in giving us information about the stage of dementia. But very, very early on we realized that actually none of these markers by themselves can be a really good predictor when we move early. If an individual has already progressed and has symptoms of dementia, it's usually too late. And all of the clinicians I work with, they'll say, if an individual already has symptoms of Alzheimer's, I know, I don't need you, I don't need models to tell me. Right? So really important where we need to integrate all of the different markers of dementia and use multimodal AI to do this is when we want to predict early. So today I want to show you how we actually work in this space of this early prediction space by bringing in different models, validating them through research, and then how we can translate them into healthcare and into clinical trials. So I won't go into the details of the models, but I can explain quite a lot about the different types of model architectures that we built. But the premise of all of this is we start with many different data types, and the first kind of layer is we use tools that allow us to extract features from many different data types. This could be blood tests, could be MRI scans, could be PET scans, it could be cognitive tests, it could be wearable, it could be any tools that we have in our hands that tell us something about the brain and its trajectories. And so these tools that we build for kind of feature engineering and feature extraction vary a lot depending on how deep they are. But the most important thing that we do before we put them into a multimodal fusion type of model is ensure that they are biologically relevant, that they are clinically relevant. Otherwise, it's very hard for these models to be interpretable and generalized. And for us, is one of the most important things is really this interpretability and generalization, so that we are able to get these tools, hopefully one day, through regulators and apply them in healthcare. So once we've done this initial kind of funnel and we've extracted our markers, then we pull markers from multimodal data into models that they look into their integration, and they allow us after that not only simply to classify, but they tell us where an individual will be in their future trajectory. We do this through a snapshot, but we also do this by modeling whole dynamics of pathways of individual trajectories. We have validated this so far across 20,000 people. This is very domain kind of specific data that we need for this work, and we have done it through research data, but also healthcare data. So what do these what do these models do? Effectively, the first thing that they do is they provide very good tools for precision stratification. Remember, we need to know where people are in their trajectory and what dementia type they have. And this is one of the very first validations. We get a score from these tools that tells us how people will progress. We're not very much interested in diagnostic labels because we know diagnostic labels come with misdiagnosis. Some of our tools, of course, are supervised, so they use labels. Some are unsupervised, they don't use labels. But the outcome of these models for us is whether people will progress and how fast they will progress. Will they move slowly? Will they move rapidly towards dementia? Or will they remain stable? And that's what you see there. The higher the score, the more progressive is the prediction that the model makes. And what you see is because we have normative data, we've done this through large-scale populations, we can then bin the scores that we get from the model and assign a new patient to a new category. And those categories are either the individual will remain stable or will progress slowly or rapidly. And you will see why this type of classification might be helpful in the context of clinical trials or healthcare. The most interesting thing, and I will pick on that a little bit later, is actually this data here. I love this pointer, thank you. It says pre-symptomatic. These points down there are actually individuals that do not have symptoms. These are individuals that volunteered for research. We have all of their data, but they have no symptoms. And what you see here is that, of course, some of them, or most of them, are predicted to remain stable, but some of them have already started progressing. Are these the people we need to be following? Are these the people that need to be changing lifestyle immediately? Are these the people to put in clinical trials that look for early targets before damage has settled in the brain? So we'll pick up on this question a little bit later. I'm sorry. So what can we do with these models? As I said, for us, it's really important to go early. And that's what you see here. So here you see data from two distributions. The one on the left, the orange one, is cognitive normal people, no symptoms. The one on the right, the blue one, is people that already have Alzheimer's disease. You can see, of course, these are easily separable. The gray distribution in the middle is people that have mild cognitive impairment, or MCI. Now, these people are early in their disease, and this diagnosis is a quite general label. There's huge heterogeneity in this mild cognitive impairment. Effectively, these are people that they went to their GP, there is a reason for concern, their family has started detecting some changes in their behavior, they get forward, they sort of get referred to secondary care, they have some clinical workup in terms of looking at some scales, there is reason for concern, but their MRI scan might not look different from an older adult aging and losing some gray matter and white matter. So there is reason for concern, but there's not a clear dementia diagnosis. The heterogeneity is huge. What we can do with the models we have is we can actually precisely split these people. What you see here is the red distribution is actually the people that are cognitive normal. These are the people that have already a D diagnosis, or Alzheimer's dementia. And what you see here is all of these are MCI people, but they can now be split effectively in 3 groups. People that are more cognitive normal, people that are more like Alzheimer's, and people that are in the middle. So already, from a very heterogeneous population with the models, we can split them more precisely. This is really important for recommendations for pathways, treatment pathways, care pathways. More importantly, actually, when we look at the profile of these 3 different subgroups of mild cognitive impairment, we see that they have very different cognitive profiles, but also very different molecular profiles. This is looking at proteomics. This means that we now have subgroups of patients that they were given the same diagnosis, but their biology, their pathology, and their cognition are very different. We cannot be treating these people the same way, and we cannot have them waiting. The people that are already progressing to Alzheimer's, we need to be treating them immediately. People that are looks like they have symptoms, but they are kind of predicted to be stable, like cognitive normal, maybe we need to be changing the lifestyle. Maybe we should be looking for co-pathologies, like, for example, maybe they have cardiovascular disease, which of course affects the brain. Maybe they have depression, which also shows symptoms like dementia. Maybe they actually have long COVID. So they need very different treatment pathways. Now, can we do the same thing preclinically before people have symptoms? For us, this is like really important. It's something that the whole field is looking for. You see, these are people that are completely stable, this distribution down here, but we can split them into stable versus progressive. They have no symptoms, but through the models, we can actually split them. You see here, this would be like their data in terms of their cognition, and you can see how we can split them in 2 distributions. The green one, they remain stable. The other ones are already progressive. I can show you the real data for this. It's just, I mean, this is real data. It's just a schematic. But similar that I show you with MCI, we have now the gray distributions are all normal people, no symptoms. We can split them at least into 2. One group that looks more like cognitive normal, and one group that looks already like progressive. And you see here that when we look at the profiles of these 2 separate groups now, the group that is more progressive has worse cognition and also has higher genetic risk in terms of APOE4. So clearly this heterogeneity is killing our diagnosis, our early diagnosis, is killing our treatments, and I'll show you that. And we can come in with these multimodal models that are already pre-trained on thousands and thousands of data, and come in and be able to stratify more precisely not only people that have early symptoms, but also people that they don't have symptoms yet. As I said, we can do this when we move, especially into this pre-symptomatic space. We have no labels. We need to know what is the trajectory of these people, so we can do it with mixed state models or neural ODEs, where we track their trajectories and we cluster in a smart way people in clusters that then show very different pathways, as you can see here, of actually progression. Some people are stable, some decline very fast, and some are kind of in the middle. And this is all projected based on the modeling that we've done. So this is what we can do with these models. But as I said earlier, for us it's really important that these models are interpretable. First, because I'm a neuroscientist by training, and I want to know what's happening in the brain of these individuals that I stratify in one group versus another. But more importantly, because this is a mandate that we have, if we want to translate these tools, we need patients, we need doctors, we need governments to understand, to be able to trust them. And so here's what we do to be able to do this. We build these models not only for high accuracy, precision, but we also build them for interpretability. That means we can open the hood, look inside. In this case, these are like prototype-based models, so we can look in their tensors and understand the contribution that each marker makes to the model decision, but also the contribution of the interactions that many different markers make to model decisions. So here, for example, this is proteomics data, and you can see that we can identify what are the key proteins. We can do that for a PPI, so protein-protein interactions, pathways, but then we can also go into the multimodal space and combine different proteins or blood markers with cognitive scores, for example. Not only our performance gets better in terms of the accuracy and the sensitivity and specificity of the models, but also we get more insight on what are the key assays that, for example, people can run in a clinic or in a clinical trial to be able to stratify patients precisely. So that's the first thing. The second thing that we are very much interested is being able to separate patients that they have different disease profiles, so different subtypes of dementia. And we can do this with these models here. You see, for example, separating Alzheimer's disease from frontotemporal dementia. And you can see we can do this with the models, and then the models allow us to understand the interactions about different kind of brain markers. So in this case, what you see is that when we predict that an individual will have Alzheimer's disease, we see that this relies on hippocampal regions, the medial temporal lobe regions, in terms of brain scans, but also immune markers in terms of molecular signatures. If we're looking at frontotemporal dementia, we actually see more frontal brain regions that seem to interact not only with immune, but also with signaling pathways, molecular pathways in the brain. Understanding these interactions is really important for building treatment pathways. So the final thing, of course, that we do is when we get from a model a multimodal score, a score that tells us where the patient is heading to based on having digested all of these multimodal data types, we need to ensure that this score, which is what we will give to clinicians, what we will give to a clinical trial, is actually clinically relevant. And that's exactly what you see here. We validate the scores against known pathology markers. You see that this score relates very strongly to a cognitive decline. It relates very strongly to amyloid, which is one of the first toxin proteins that increases as dementia risk. Relates to atrophy in specific areas in the brain. Relates to genetic scores. So all of this gives us actually information about interpretability. And the final kind of part of the talk, and hopefully I still have a little bit of time for that, that I want to focus is how we translate these tools to healthcare. What can they do for us effectively in that translational space? And the first thing that these tools do for us is they make dementia visible early. What you see here is two patients, and if you look at their MRI scans at a very early stage, actually they don't really differ much. It's really hard by the naked eye to be able to tell, even for an expert neuroradiologist, whether these people will have different trajectories in terms of their brain health. But what you see next is when we look at the multimodal data through our tools and we get a score, you see that actually this patient, the model predicts that they will remain stable, while this patient, the model predicts that they will decline rapidly. This is again really huge in terms of stratifying people based on their prognosis rather than just on what we are looking at right now, because that means they need very different treatments. So how do I know, though, that the model is right? And how do I know actually that these models that we built in research data will translate in clinical practice? Well, to do this, we went to memory clinics. And we started from the UK, and then actually we went to Singapore, because Singapore has digital records for a very long time, and we were able to track patients over time, look at their initial data and predict, and then check their future paths. So what you see here, in fact, is data from a memory clinic, and we didn't train the model was pre-trained. They gave us the data. The model looked at the data of individual patients, and the model gave each patient a score. And what you see here is patients with the highest score were already actually diagnosed as Alzheimer's. We didn't have the labels. We were blind to the labels, to the diagnosis. We opened that later on. Then you see kind of in the middle here, the intermediate scores. These are patients that they already diagnosed as mild cognitive impairment. And then these lower scores relate to individuals that they were already labeled as cognitive normal. So maybe symptoms, but no real pathology. So for us, this was the first actually validation in real-world healthcare data. These are people that went to their GP, they got referred in a memory clinic, they had a cognitive test and an MRI. In this case, these are the type of data that we put into the models, and we asked them to predict. But the hardest question is to know whether we can actually validate the predictions of the model over time. So our models make these predictions at time 0 at the first patient assessment. How do we know that the models are right? So we did this with longitudinal data. We had about 10 years data You see here up to 6 years because unfortunately patients, as they progress, they pass away. And that's the 6 years is where we have most of the data. So we focus in this window. And we ask the model to predict at time 0. So we give the model the initial assessments that the patients have here. And the model makes predictions on whether individuals will remain stable, or they will rapidly progress, or they will slowly progress. And then we open the data over time, and you can see that people have actually different trajectories. And this trajectory matches the initial predictions. Within 12 to 18 months, we can see actually the change. Some people, 50% actually of the people in this sample, they remain stable. We predicted that, and they did remain stable. 15% of the individuals were actually predicted to be rapidly progressing, and then 35% were slowly progressing. And you can see the validation through the data. Really interestingly, actually, this would have been the prediction based on a Cox regression of individuals that were given the diagnosis of mild cognitive impairment. All of these individuals were given this diagnosis, mild cognitive impairment, at their first assessment. And you see here, that would have been their trajectory based on longitudinal data. But you can see when we split them based on the model, they have actually really different trajectories. And it makes a huge difference to be able to tell a patient and their family that, yes, you might have symptoms, but I predict with fairly good certainty that you will remain stable, and therefore your symptoms are not because of dementia pathology. And it also makes a big difference to be able to tell a patient and their families that you will be declining really rapidly, so any treatments, we are going to proceed with them right now. Rather than saying, come back in 12 months, we will do another cognitive test and another MRI scan, and we will assess. It might be too late for these patients. So really interesting in dementia. I'm sure you have all read about it in the papers. We've now had a breakthrough. We have blood tests that they can detect proteins in the blood, and this is really a breakthrough, that are actually associated with amyloid, one of the toxic proteins in the brain that accumulates in the brain and is high risk for dementia. That means we cannot do better prediction, but we can do prediction faster and in a non-invasive and hopefully less costly way. So we can now go into the models and put in blood tests and combine them with cognition. We also combine them with other proteomics markers. And you can see we can do really well in terms of predicting these trajectories. But we can be even more precise than these blood tests. So what you see here is initially you see here on the left is what would happen if an individual had a blood test and we collected the p-tau217 protein in their blood. We looked at the concentration. Some people will be negative, some people will be positive, and then actually in diverse populations in real life, we have quite a lot of people that fall in this intermediate category. So what happens now, and this is hopefully moving into healthcare very soon, we have recommendations ready, is if an individual is negative, they are told you're really of a very, very low risk, you can go home. If they are positive, then they are sent for a PET scan to validate this. If they're intermediate, they are called come back in a year. They are told come back in a year. Now, what you see here is what we can do with the models, and you can see that we can stratify much better with the models, especially in the intermediate space. If you can follow these green tracks, right, you see that we get people that they were given that prediction from effectively a blood marker. They were told come back in a year. But some of them, you see, they are moving really fast, so they will be too late in a year. Some of them, actually, we predict that they don't have actually dementia pathology, and we should be looking at a different treatment pathway. And similarly, you can see that we can do this also for people that they are in the negative space, and people that they are in the positive space. We can stratify them much more precisely. So again, these multimodal approaches can do not only better in terms of their accuracy, but they can reduce false negatives and positives, and they can create much more precise predictions about individuals in terms of their longitudinal trajectory and their treatment pathways. So the final thing I want to talk to you about is clinical trials. So we need better treatments, and we need them now. We have been waiting for 30 years, and we had huge cost in terms of R&D. More than 40 billion has gone into R&D development, and for 30 years we had one failure after the other. We now have 2 disease-modifying treatments the last couple of years. They are not potentially the best, but they provide great promise for what to come. These are treatments that they are looking in reducing amyloid in the brain. But the major problem we have in clinical trials is what we call the Goldilocks problem. We need to find the right treatments for the right patients at the right time. And we need to be able to treat patients early with precision stratification. So what you see here is we worked with top pharma, we can name them, they're AstraZeneca, when they used to have a neuroscience team. And we worked with their neuroscience team and their data science team. We published the work, so it's in the open domain. And we worked with a trial that had actually failed. This was a BACE1 inhibitor that decreases amyloid, the first toxic protein in the brain. And effectively, this was a phase 3 trial. This trial in the phase 3 costed only $350 million. That means, this trial had costed billions. It started from preclinical, from animal models. It went into phase 1, no toxicity, went into phase 2. The trial got powered up. There was great hope. This was one of the best BACE1 inhibitors, actually, in terms of showing potential for reducing decline, while other inhibitors had shown actually worsening. So why did the trial fail? The trial failed not because the target didn't meet the biology. Actually, the target did the right thing, reduced amyloid in the brain. But patients had no changes in symptoms. There was no changes in cognition. And of course, the FDA wants to see changes in symptoms to approve a drug. So the trial 2 years later closed. So we went in with pre-trained models. It's really important because we need these models to be trusted. We don't need to be manipulating the data, the trial data. And we re-stratified the patients, and actually we saw a huge effect, and I'll show you the results. This is the initial trial data. What you see here is this data is really not, you can't really split them based on different markers. And as I said, what you see in the first graph here is the patients actually cleared amyloid in their brain as the target was expected. But there was no difference in terms of their cognition. The first bar, the black bar, is the placebo. The other two is different dosages of the drug. Now we came in, and what you can see is we can stratify people, and this is from their baseline data as they sign up in the trial. We can stratify them based on slowly versus rapidly progressive. Now we have two groups to look for drug effect, and this is what happens in the first group. The first group is the slowly progressive group. They clear amyloid in their brain, but more importantly, they actually show a decline, a reduction in their cognitive decline. These drugs don't make your cognition better, but they reduce the decline and they slow it down. And you see here that actually we have a significant reduction in decline for the slowly progressive group. Now this didn't happen for the fast progressive group. And as you can see here, this fast progressive group is actually most of the people. So they bias the sample. Right? Why did that happen? Potentially by looking at other markers, we realized that the people that were predicted to be slowly progressing were much earlier in the neurodegeneration pathway. That means 2 years down the line, when the trial stopped, these people were on the drug and they could show a cognitive benefit. While the people that they were predicted to be rapidly progressive, it was too late. They were clearing amyloid, but it was too late. We have a brain damage effectively taking place, and these drugs don't actually, they clear the protein, but they cannot really change the symptoms. So by looking a little bit more in statistical models, you can see how we can shift people that are slowly progressive into stable through drugs like this by stratifying them much better. And you can see how we can actually get those trials to be faster and cheaper, smaller size, right? They didn't need in this trial, 90% of the sample could have been reduced. They didn't need that many people. That means, if we could use this in phase 2 when we power up the trials, we can have multi-arm trials. The people that are rapidly progressive could benefit by different drugs compared to the people that are slowly progressive, and they could be actually running a trial with one placebo group, multiple targets for different groups, for precise stratified groups. Why is that really important? Currently, there's a huge strive in dementia to develop new treatments. There's a huge strive to bring clinical trials to the UK, which is really important. We have more than 180 targets that are going into clinical trials. if we can do much better in the stratification, the patient stratification and inclusion criteria for trials, we could really have many more treatments for people that are stratified much more precisely and therefore have the right drugs for right people in moving into this precision medicine approach. So I'd like to close by giving you kind of some hints. I hope I've given you some evidence how we can use really multimodal AI tools in precision healthcare. We can bring them into the clinic. We can make a difference in supporting clinicians to make better decisions about the diagnostic and the treatment pathway, hopefully saving a lot of costs for the NHS, but also targeting our resources to those who can benefit the most and who need them the most. We can then accelerate drug discovery by moving towards more precision medicine approaches, which is really critical in our pathway. And finally, we hope that we can also move into the prevention space by looking at before people have symptoms and how we can predict precisely brain health trajectories that will allow us to intervene early on and create more healthcare opportunities rather than sick care burden to society. So I'd like to close by thanking everybody. I'm standing here today, but there's really a cross-disciplinary team behind here that is really driving forward this research. It takes many brains and many minds. Clinicians, engineers, computer scientists, AI experts, neuroscientists, everybody come together to really support this effort. I'd like to thank my team, but also all of the funders who took a leap of faith and gave us funding for the last kind of 10, 12 years when we've been developing this before anybody thought that this is not completely crazy in science fiction. Thank you so much for inviting me and listening in, and I very much look forward to your questions and possible collaborations in the future. Thank you.
Yes, thank you, Zoe, for the fascinating talk. Do we have some questions?
Thank you very much. It's absolutely fascinating. I was wondering whether you're also looking into translating this methodology into other types of diseases, stratification?
Yeah, absolutely. So we haven't done it. We've got our hands busy and full. But these are, so we kind of use this as a use case. I can tell you a little bit how this happened. About 12 years ago, I'm a neuroscientist, as I said, with strong computational background. But you know, more than like 15 years ago, I was giving a talk on brain imaging and what computational tools we can build. And at the time, you know, we didn't used to talk about AI. We used to talk about, you know, the initial kind of machine learning models that people were building. And a clinician came up to me and said, well, you know, I have people in my practice and I can't do anything for them. You know, I can't even diagnose, or I don't have tools. You know, is there anything that we can do in an experimental program? So I didn't know anything about dementia. And this was a neurologist consultant. And so we started working together, and then I realized the US was opening data funded by the NIH for many, many years, and this was the very first data sets. So we started working on this, and of course, you know, it was a fascinating area. And initially, everybody I talked to, they said, why would you want to do this if I was to have dementia? I don't want to know. I wouldn't want to know, right? But now we have got to a point that we can't say anymore, I don't want to know. It's so prevalent, and really we have potential for interventions. So it's kind of, that was the journey. But of course, you know, we're working also with researchers that are very much interested in mental health disorders. Again, a space that is kind of more close to neuroscience that I know a little bit about. But this could be, you know, really extrapolated, let's say, in many different disease models. I always like working with people that have the domain expertise, people that they generate the data. There's a lot here that that kind of real cross-disciplinary teams can do. We speak different languages. And then often I find myself in the middle doing the dictionary and doing the translation. Like I'll have people, speaking in markers and people speaking in effectively data types and entry values in a code, right? And it's really important to be building that cross-disciplinary translational language so that we know what are the important questions. Also really important, what do the patients and their families want, what is important to them, and then use tools like that to answer these questions.
Great. Some more questions?
Yeah. Hi, yeah, thank you for a really excellent talk and a really amazing bit of work. My question is, for the clustering, what do you use as the kind of point of diagnosis, for example, for like Alzheimer's or dementia? Because was it like an ICD code or there's like 20,000 odd patients? So what was the kind of used as the kind of end point, if you see what I mean?
Yeah. This is actually a really tricky question when you in the space of dementia. So there are ICD codes, as you say, and we can use that. But a lot of times, people will be diagnosed simply by clinicians that they might have just a scale. So sometimes we have labels, sometimes we have ICD codes, and sometimes we have nothing. And that's why we're using unsupervised models. But where the labels come, that you might have spotted on the slide, is for validation. The algorithms will give us, so for example, these are state mixture models, right? And we get the clusters, and then we want to see, okay, how can we profile these clusters? Why people end up in one cluster versus another? We create also kind of a membership score, right, in terms of probability of assignment to a cluster. And that's where we can use diagnostic labels. We open the labels and we look, oh, this cluster has 80% people that already have that diagnosis of AD. But the problem is these labels, all of these, the ICD codes or anything that a clinician, for example, was able to give, they carry a lot of misdiagnosis because of this problem of heterogeneity. And the earlier we go, the harder the diagnosis, therefore the higher the heterogeneity and the potential of misdiagnosis. So we know from literature that up to 35% of the cases are misdiagnosed, especially in kind of diverse populations where there's not enough information or not enough tools. So we try to avoid labels and use them more for kind of validation when we have them. But sometimes we create those labels. So if we are lucky enough to have a lot of data, different types of data, then we use kind of diagnostic frameworks from research. So we will combine a cognitive score with a genetic marker and with maybe a PET scan if we had any proteins markers, amyloid, for example, or tau. And we create labels that might be a little bit more sensitive. But the problem is we really don't have, if you want, very much of a ground truth. If we have PET scans at the end and we have tau accumulation in the brain, that's the best we can do. But these are very expensive. Only 2% of patients diagnosed will get a PET scan. So as we go into healthcare, the best would be to be able to validate with labels outside with large kind of cohort data, and we have more and more data opening up. And then when we go into healthcare, build more kind of unsupervised or semi-supervised models that allow us to do without labels, but building that validation of the clusters we get, then they are meaningful and robust. Thank you.
Any more questions?
Thank you, Zoe, for an amazing talk. It's very close to my work as well. The question I had was about the clinical implementation. As we know, the NHS data is fragmented, and your model used different modalities. What were the barriers you had in getting the data to link together for each individual patient? And what were the practical implementation advice that you would give?
This is a really tough question. I had no luck, is the answer. And I'm actually very passionate about this because I believe that we don't just need data, we need linked data. Exactly for what we were just kind of discussing in terms of the validation, right? If we only have medical records, we can actually do quite a lot from medical records because we have a lot of rich copathologies in medical records, especially when we go to secondary care. So we have kind of worked on a tiered system where we start with primary care, medical records. We make the initial predictions and then we enrich. We go into secondary care, maybe we have MRI, maybe we will have blood tests, and then potentially if individuals have volunteered for research, then hopefully we can link in brain scans, PET scans, all of that, right? But the governance currently is really difficult to do in local trusts. And although I know the clinicians and they can tell me what each patient has, we cannot have access. And I think this is a really sticky point in a way, and it's something that we really need, in a way, strategic initiatives to resolve. But I think there's great hope in the UK. I think the government has now realized the importance of linked data, and so the new HDRS effort is really, really promising, effectively hoping that we can link medical records with genetic data, and this will be a great starting point. So if we can all, kind of lobby for a common goal, then I think these models, we will be able not only to build them to be more precise and more robust, but also to validate them. And this is really important. Otherwise, nobody's going to trust them. And the moment that we make one single mistake, we are going to bring the whole field down, not only in one disease, but in the whole disease. If AI makes a mistake somewhere and it's been applied to a patient, you don't want to know about the legal, implications of this. And therefore, as scientists, we really have an obligation to build robust tools together with opening this data, this linked data, and working together. I hope that we can move this forward. Clearly, I think there's more awareness of these issues, but we're not yet there, but I think we're moving in the right direction. We do really need to accelerate. I mean, every time that you see a patient, they can't wait for another 30 years. They don't have that, right? And it's really heartbreaking. Yeah.
A quick follow-up. Good luck with the blood biomarker that you're working on. I hope that comes into the system. If it does, would it be in the primary care?
Well, the current recommendation, at least in Europe and in the UK, is that it will be secondary care because of the issue that I've kind of pointed to, that currently needs interpretation by a specialist. So we do have cutoffs now, and we have two cutoffs, one at the low end, one at the high end, so we can get people that they are negative positive. But in general populations, not in research where the patients are very kind of selected, in general populations we do have a large intermediate group. So what are these boundaries? How do you communicate these to patients? What is the pathway? And so potentially the blood markers are coming in hopefully to meet the gap we have because of PET scans being very invasive and very costly, and giving clinicians another tool to be able to make their decisions a little bit more confident. But as I showed you, if we can make that even easier for clinicians and more precise for patients by bringing in these multimodal approaches. Yeah. So hopefully this will be in secondary care soon. And we will be able to ingest this data together with medical records, and that would be really amazing. Yeah.
Thank you.
Thank you.
Yeah. Thank you, Zoe. So maybe one more question. Yeah.
Sorry, I want to thanks for the speech. I have a question related to the treatment and maintenance for the disease that already diagnosed. So how far do you think we stand that AI can apply for, for example, app for the people or the family that have the patients that can maintain and treat their symptoms at home and support them? Because I believe that it's a big burden if you already get diagnosed or you have someone in your family have this. And do you think it's even possible? Other non-communicable diseases that we might have, because I have to say, we already have seen a lot of apps that are working on a lot of diseases, but they are not always working that well as we expected. So what do you think about in dementia? Thank you.
Yeah, thank you. It's a really, really challenging problem. As you say, there's lots of apps, and you can keep checking your cognitive health and everything. And there are many more other tools. For example, people are now wiring homes. You can have a device. This is a really interesting development from UCL. You can have a device under the mattress and measure, for example, sleep patterns, respiration. There are more and more tools that are being developed to facilitate at home, maybe no diagnosis, but at least kind of initial indication of symptoms or tracking individuals. A really important thing that we hear from patients, once, as you said, somebody's been diagnosed, is what they want to know is when they will have a change. They might be stable for a little while, but when is that change going to happen? Because usually that change creates sort of a crisis event. They might start falling more, they might be getting lost more, and that means they might end up being hospitalized. And patients and families really care about avoiding these crisis events. They know that they might not be able to get better, but can they avoid these crisis events? So that monitoring is really important. And that monitoring is really hard to do within the healthcare system. The reason for that is simply that the healthcare system is overwhelmed. 65% of people don't even get diagnosed. So, and nobody wants more referrals from GP practices to secondary care. It's a very complex puzzle, right? But so people don't get monitored. So they will miss those changes. And if they are seen in another 12 months' time or 18 months' time, it's too late. They've already progressed. They already deteriorated in terms of their symptoms. So it's really important to be building these monitoring tools. And I think when are we going to be ready? I don't know. I think there are quite a lot of tools already that are being developed and they are being tested, trialed. I think as a kind of multimodal AI community, where we can really come in is synthesizing again the data across these tools, potentially bringing platforms where this data can come in and being synthesized. And why is this really important is because we know that each one of these tools is not going to provide the precision markers that we need. So, for example, if you have your watch, and it tells you that consistently maybe your heart rate has changed or you're not sleeping, what is this? Is this a warning for dementia? Is this a warning for something else? Right? Is it that maybe you kind of have a long-term infection running, or you're really stressed, or you're maybe doing some cognitive apps and it feels like maybe is it that you're depressed? Is it that your mood is changing? Is it that maybe you do have early signs of dementia? But we're going to need to be able to combine these kind of monitoring signals with biomarkers. And blood tests at home, I think, not happening soon, but maybe they will be happening in community centers one day. As I said, we're starting from secondary care, but community centers, is something that probably we will be able to see fairly soon. And again, if this data can come together, maybe in healthcare, federated type of systems, we can bring in the tools. This is our kind of obligation and mandate. We can bring in reliable, trustworthy tools that then we can make better predictions out of this integrated data, and I think then we will accelerate and we will move fast. We are not far. We used to be further. This is not science fiction. This can happen. But it really, I think, takes a lot of kind of like-minded people, and it takes what we heard earlier. We need to be accelerating science in a different model. The model that we use to work in science is too slow. And the funding model needs to change, the publication model needs to change. We need to change as researchers, and we need to be driven more by these real-world problems and really making innovation our primary aim in research.
Great. Let's thank Zoe again for the excellent talk.